All right, everybody, we're going to do the circular motion notes, which comes from pages 208 and 209 in our textbook. And so I have all the notes written out for you here. It's only 2 pages, but there is a lot of information in here. And I have some really good videos to watch. One is about angular velocity, and then the other is about circles and pi and phi, I think it's called. There is a lot of cool stuff related to circles, and I've always kind of shied away from the topic of circular motion. I found it kind of difficult, but since we have extra time, I'm going to try to really put something good together to explain it. So, working with circles, we have to be good at degrees, measuring angles, and radians, which you should have seen in geometry and trigonometry. So hopefully you have some basis in that. And let's look at the notes. So circular motion examples: Earth's orbit, a turning wheel, spinning top. So anything that moves in a circle, right? So we got the orbits of the Earth, we've got wheels and machinery. Think about if you have a vision of what some machinery looks like, there's always like wheels and cogs, right, that are rotating. So all of that is very important, especially the cars, right? Everybody loves cars. Got to have the wheels spinning. All right, so what is angular velocity? It's the rate at which a rotating object spins. And the symbol for angular velocity is omega, and the symbol for an angle is theta, right? So it's the amount that the angle changes per unit time. So here's our formula for angular velocity. So the angular velocity, it's kind of like a W, equals the change in angle divided by the change in time. So this thing is going around in a circle, and we're looking at the angle that it's going through and how fast is it going through that. So what is a radian? So we know about angles, right? We got like 0-degree angles, we got 90-degree angles, we got 180 degrees, and then a full circle is 360 degrees. Well, radians, it's a more natural unit of angle than a degree. And 1 radian equals 57.3 degrees. So there is a ratio. So this is where it gets interesting. So you have a circle, and then we have a radius, right? So here's my radius. So the distance of one radius along the circumference in r, that is 1 radian. And usually that corresponds to an angle of 50, oh, I hate when that happens, 57.3 degrees, and there's formulas for all that. So, and then it relates to the circumference, right? What's the circumference is 2 pi r, right? So there's all these different relations. Counterclockwise rotation is positive, clockwise rotation is negative. So if we go clockwise, right, clockwise is this way, that's negative, and this way is positive, right? Yeah. And so if we start here at 0 degrees, and then this is also, if you go 360 degrees, this is equal to 2 pi. So 360 degrees is equal to 2 pi. So half of 360 degrees is 180 degrees, right? So that's over here. That's just pi. And then 90 degrees is pi over 2. And then I guess the bottom is what? I don't know. I forget what the bottom is, but we're going to look at that a lot later. We're going to go over the unit circle. So there's a relationship between radians and degrees, and we just have to be cognizant of that. And this pi equals 180, that is usually what I use to transfer or transform using dimensional analysis to go from degrees to radians or radians to degrees. So we know that pi is 180 degrees. So let's say I have an angle of 65 degrees, and they say, what is that in radians? Well, I just use dimensional analysis and say, well, 180 degrees is equal to pi radians. So then I multiply across, and you could do it in, you could just use your calculator. Let's see, what's 65 divided by 180? You could also use Desmos, right? Let's use Desmos. What is 65 divided by 180? Let's see. See, I was doing some of the work. 65 divided by 180, 0.36 pi, but what if I multiply times pi? So I got 1.13 radians, 1.13 radians. So annotate, so that's 1.13 radians. So 65 degrees is the same thing as 1.13 radians. So yeah, that's a crash course in radians and degrees. So sometimes you have to transfer between degrees and radians, and I would use dimensional analysis using pi equals 180 degrees. Clear all that. And I'm going to post this video later, so if you want to watch it again for another explanation. All right, so then we have an example problem. The Earth rotates once every 24 hours. What is the angular velocity in radians per second? Okay, so what did they give us? Well, we know that in 24 hours, it rotates 360 degrees, right? A full rotation. So we know that it's 2 pi every 24 hours. What is the angular velocity? Well, it's the change in angle over the change in time. So 2 pi over 24, right? But then we don't want to know hours. We want to change hours into seconds. So in 1 hour, there's 60 minutes. In 1 minute, there's 60 seconds. So this is our old dimensional analysis coming back into play. So minutes cancel, hours cancel. So now we have radians divided by 60 seconds. So we have to put all this in 2 pi divided by 24 times 60 times 60, and I get 7.3 times 10 to the negative 5 radians per second. Let's put this in Desmos. 2 pi divided by 24 is 60, 60. So 2 pi, so here you just have to type in 2 pi divided by 24 times 60 times 60. And then it gives it to me in a long decimal. So I would accept this answer. You could just put that answer in there. I changed it into scientific notation. And we're probably going to play with that too, do some examples of scientific notation. But I would accept this answer. 0.0000 0.00000727. And you could put, 7.3 or whatever. All right, so that's the first example. And then we have linear velocity. So this goes into like how fast is the wheel moving in a line. So this is related to Um, this is related to a wheel that's turning, and we know the angular velocity, but how fast is it going? What's its velocity? I think what it's going to look like is like if you have a wheel and if you have a point on the wheel, what is the what is that velocity? So, what is rolling motion? A rolling wheel has both linear and angular velocity. Linear velocity is the circumference divided by the time it takes to make one turn. So it's the circumference, which is 2 pi r, right, divided by the time it takes to make one turn. So this is equal to angular velocity times a radius. So that's interesting. So linear velocity is your angular velocity, which we just learned about, times the radius. And so then they asked the question, why did old bikes have such large wheels? Remember they had like a small wheel in the front, and then they like had a big wheel in the front, and people would sit up here really high. They didn't have gears and stuff. Um, so if we look at this equation, velocity equals um, angular velocity times radius. The bigger the radius, the bigger the velocity. So that makes sense that they would want a big wheel if they didn't have gears, right, back then. So if you had a big wheel, then you could go faster with less effort, which is the reason why they had large wheels. But then we invented gears, right? And now we don't need such big wheels. So then it says a car has wheels with a radius of 30 centimeters. What is the angular velocity of the wheels in radians per second and revolutions per minute when the car is moving 30 meters per second? Okay, so see, this is telling us that a wheel on a car has a radius of 30 centimeters. So then, and we know the angular velocity. No, we don't know. They want to know what is the angular velocity. So we don't know what angular velocity is, but we do know the velocity of the car. So they're saying that this thing's rotating and each point in the wheel is going 30 meters per second. So if one part of the car is going 30 meters per second, that means every piece on this wheel is also traveling at that speed, right? So um, if we know the speed that's going in a linear fashion, it's going straight, right? Then we know how fast is that wheel turning? What's the angular velocity? So they gave us velocity, they gave us the radius. We want to know what is the angular velocity. So we just take the velocity divided by the radius. So that's very simple, right? 30 meters divided by, the only thing we had to change was centimeters into meters, which is you just move that decimal 1, 2, right? To go from centimeters to meters. So 30 divided by 0.3, you get 100 radians per second. That's the angular velocity. But they didn't want radians per second. They wanted revolutions per minute, right? So once we have that 100 radians per second, then we say, well, one revolution is how many radians. So these two are the same units, right? We know that one revolution is 2 pi. So we got put the 2 pi down there, put the one revolution, and then we know that it takes 60 seconds to equal 1 minute. So that's why we're just converting, right? So then we get the final answer 954.9 revolutions per minute. So a wheel is turning 955 revolutions per minute when you're traveling at 30 meters per second. So the wheel is spinning really fast, but we've got a nice velocity of 30 meters per second. So yeah, so see, it is pretty complicated. But so let's get these. So it's just vocabulary and notes, and then I have some really good videos to watch that explain all of this a little better than I did probably. You could also read the book. That'd be a good idea. But this one is more an explanation of physics, and this one is like kind of the mysteries of circles and angles and all that stuff. So very good stuff. Um, I would watch the videos and do the notes and take a look at the book. Let's see, here's the book. This is page 208. So read it if you need to. And then next time we'll do some practice problems. So it's only 2 pages, 208 and 209.